for is how do you capture the flow field of a shock wave, which is of such short duration, if also you want to find out what is the density change in it. And eventually we'll see from that we can back out so many more interesting things. So to start with this talk, for the formal purposes of a talk, I have an outline here, which will look at how do you visualize any density change, and then come to the main theme of the talk, which is this funny sounding word. We'll come to why it's called so, and finally look at very new applications of BOS, because if you want to stay relevant, you have to say that you are also part of the machine learning, artificial intelligence trilogy. Of course, you have to have NI before AI, or they say Einstein before natural. So anyway, so we start first with what is the propagation of it, the light propagation. This is all high school stuff, so I'm not going to dwell on it too much. Light coming through the windows, you know what happens, it gets filtered out, certain wavelengths get filtered out. One of the key things in any optically transparent medium is the refractive index. The refractive index, essentially, to recap, tells you how the speed of light changes when it interacts with matter. Matter can be the gas, it can be glass, either. So essentially, this refractive index is greater than 1 because the way it is defined as C0, where C0 is the speed of light in vacuum, which is invariant, and C is the speed of light in the medium. So you realize, since the speed of light in vacuum is absolute, it always has to be greater than 1. Now, gases also, because we are talking of optical transmission through transparent gases, they bear a linear relationship between refractive index and the gas density. This essentially says that, this is called the Gladstone-Dale equation, and essentially it says that the refractive index is related to the gas density by a constant known as the Gladstone-Dale constant, which is like 0.23 centimeter cube per gram. You can figure out the units. So essentially it's a function of the gas, and so this is how it is. So having said that, if one were to look at the refractive index, you will find that it is only very weakly dependent on density. So in fact, if the temperature of this room changed a little bit, you would not even see any changes in the refractive index. In fact, if you increase air density by 2 orders of magnitude, that's 100 times. I make the air density in this room 100 times more than it is now. You would see only a 2.3% increase in the refractive index. So what is the implication of this? It means you need very sensitive optics. And in engineering, as you would have learned, anything which requires very sensitive instrumentation is, I would say, loosely speaking, is usually lab science. It is not science out in the industry. Industry needs robustness, repeatability, and imperviousness to all kinds of vibrations or real world noise which you have now. Right. Okay. So the whole talk is not going to be like this. So those of you who are already feeling sleepy, stay awake for a little longer. This is required so that when I use this terminology, you know what I'm driving at. So suppose you have light as a plane wave front. So then you have here a negative vertical density gradient. What does that mean? It means that the rate of change of refractive index in the y direction is less than to make the refractive index in the glass. Or think about it, that this is a glass and there's basically a temperature gradient of water, inside. So obviously the wave front which is coming out, which is parallel, will still deflect. It will bend. So when it bends, what you will see is the distance, of course, the wavefront moves in time t is c times delta t, that's the velocity times time is the distance. So the big takeaway here is the refraction angle, which denoted by delta epsilon. So you had a plane wavefront which went through a medium which had a varying refractive index, and immediately you had an angle imposed on it of refraction. And this angle you can just calculate by geometry and arrive at some number. Okay. So what's the takeaway from that? Essentially, what I'm driving is you can find out the ray deflection in both the x, which is into the plane of the board, and the y directions. Right. So with my rate of change of this refraction angle depends on the refractive index gradient, which we already agreed is varying from bottom to top. So far, so good. What we need to here remember is that the refraction is caused by the gradients of the density refractive index, and not so much by the value, absolute value of the n itself. So, once we have said all that theory, we need to know how do we measure. So we need optical methods. So optical, now I assume none of you have heard about shadow graphs and Schlieren. I assume none of you have heard about shadow graphs and Schlierens, right? If anyone has heard, they can raise their hand. No, okay. So basically, we already proved that your light ray gets deflected when it goes refractive index. So if we can capture what is the deflection the light ray undergoes, then obviously you can quantify the change in refractive index. The refractive index is related to the density by the Gladstone-Lin constant, as we saw on the second slide. So you can find the density field of the circuit. So it goes. That's why I say a qualitative or quantitative. It is. You will see that while it's easy to visualize, it's not so easy to quantify. Right? Qualitative inferences are easy. Quantitative inferences are difficult. You can do so by interferometry, but that's a technique which is best left to within labs on vibration isolation tables and such. It's a pain in the whatever to set up a method. So essentially, if you look at this, to speak graphically, you have your incident light, you have your disturbance. When I say disturbance, I mean change in density field or temperature field, which is causing a change in the refractive field. There is a problem when there is both a change in density and temperature. How do you decouple the two? We'll handle that later. So basically, you have this disturbance, and you have say a theta star, and you have a Q star. Essentially, a shadow graph looks at the Q star, and Schlieren looks at the deflection angle. Right? And will not bother about the interferometer because it's barely there. So you see, like you can see from any candle, and you have here the shadow graph, you have a Schlieren, and you have an interferometer. So the shadow graph, essentially, from what we saw here, from simple geometry and the previous slide, it is looking at the second derivative of the density. The Schlieren is looking at the first derivative. The interferometry, in contrast, is actually measuring the density itself. But like I said, interferometry is very, very difficult and time-consuming to set up because essentially it's a path difference. And when we are talking optical paths, you should remember it's a function of what's the wavelength and how wavelengths will constitute in lambda. You guys have all done these things in your high school, beginning undergrad labs. You remember how difficult it was to get those fringes. So doing it on an industrial level setup is no. So we go to what's called the So we go to what's called the slave. So some of you may be wondering about what this word is. So this word Schlirren comes from the German word, a word called Schlirren, which essentially means optical inhomogeneities. So there was this person who first looked at how do you quantify, because Germany used to make the world's finest glasses. This was way back in 1800s. And how do you quantify how good is this glass? So I'm sure all of you have seen a window pane and sometimes seen that there is most of these pins are very good. So there's a small flaw in that. So, and that essentially to quantify that, he set up a system which he called as to find out the Schlirren or the optical inhomogeneity in the glass. So essentially that got caught on and became a very nice tool for finding out optical inhomogeneities in any system, and that's now called Schlirren or Schlirren images. So essentially, essentially you have here a point light source. So you have here a collimated beam. You know, if you put a point light source at any questions so far? No. Okay, everyone is awake. So you have a parallel beam, and you have a not so uniform field. When it goes to, you have here the rays are again collected by a collector lens and focused down to a point. At the point you introduce a knife, we'll come back in a minute. Why am I putting a knife edge here? And you get a pattern on the screen which is called a Schlirren. So this essentially is what you saw in the previous image. You essentially can get this central image by central. Yeah. So this is the setup. So it is the basic Schlirren setup. Very, very simple. All you need is very high quality two lenses and a point source. Earlier it used to be a big deal to get a point source. Today with LEDs, no longer a big deal. So you can just essentially set up your own Schlirren anywhere at home or at college or anywhere. So you will get a pattern. Okay. So you could, in fact, have a row of LEDs, and this is called an extended light source. Basically, then you have to have similar cutoff. So all of you have seen your tiny LEDs. Suppose I take a whole array of those LEDs. Then for each LED, I have to have its knife edge. Now, a knife edge is essentially an aperture. It can be a horizontal, blade, or it can be an actual traversable slate. It can be a circular aperture, anything to cut off the rays. We will see why basically it is to be cut off. Maybe before that we show in this. Essentially what happens is you have the light rays from the top and the bottom of this extended source, or even from a point source traversing to the slave. Now you know from your basic glass slab experiment, the light rays are bent towards the normal when they go to higher density media, and so when that happens, some of those light rays are bent down. So if you end up blocking those rays which are bent down, you obviously get a gradient which is displayed on a screen or with your eye or any photograph. This may all look like magic, but it is not really. It is very straightforward. As long as you have a collimated beam and you put a candle out there, you can get a very nice picture. So, essentially, it is the displacement of the source image that separates those rays which are refracted by this optical inhomogeneity and from the rays that provide background illumination. So, and these rays are cut off by the knife edge. The knife edge is nothing more than a razor blade can do this as well. And the Schlirren image shows the shape and strength of that. Okay, so far so good. This is all conventional Schlirren. As I'm doing this only so that you get a background or you get a baseline for which to compare what we are going to look at next, the VOS. So the sensitivity, obviously with any instrument you have got to have a sensitivity, you got to have a contrast value in optics. So the sensitivity and the contrast just depend upon the focal length of the lens that you choose. The larger the focal length, better it is, and the larger the aperture also, the more collection area it has. So you can stop or down your aperture to very small values and get good contrast. You can have variants of these. I will not bother you with them. Most lab things are ZST, simply because you have to have it off axis and you use a pair of mirrors as collimator as opposed to lens. You will ask me that all this while you were saying convex lens, why did you jump to a mirror? Well, that's simply because it is easier to make a perfect or near perfect mirror than it is to make a lens. Because lens you have to grind two surfaces, you have to have very good optical transparency, the lens has to be supported, which is difficult. So if it's a mirror, you only have to polish on one side. Most mirrors are not even glass. They are most of the time there are some copper, some kind of vapor deposition of alumina or something on a very nicely machined surface. They are not even glass. So you can make very nice mirrors, whereas you may not be able to make very good lenses. So you use mirrors. Okay. So let us start now to see something more interesting. So this is an example of a Schlieren. This is flow through a nozzle. It's called an Aerospace nozzle because it has a spike in the center of the nozzle. So you can see how the gradients are done. One is a Schlieren, one is a Jagadeesh. This is a projectile fired at 4 times the speed of sound in a reactive mixture of hydrogen and air. This is from Settles. There's an excellent book on Schlieren and shadowgraph techniques by Settles for those who are interested. I think it is available on any of the PDF sites also for free download. So, and this is shockwaves over elliptic cone. We will come back to that in a little bit. So this just shows how it looks like. You can have essentially time-resolved flow fields. This is a flashed wave from a shock tube which impinges on a flat plate. This can also be something like launch vehicle liftoff. So you can see it again. So you can see the advancing front and where it impinged on that. So you can see very, very good variations in the density field out there. Okay, this is a cold flow, so the density variation is only due to the essentially the pressure changes out there. It's compressible. So I think I have convinced you that you can, in principle, visualize density variations in air with a dedicated setup. Can you do this only in the lab? No, not necessarily. This is while this is in a wind tunnel. This is the space shuttle. This is of a gun being fired. So we'll come back to this gun being fired later. But essentially, this is the bullet, and this is the muzzle flash. So the bullet soon will exit this and have its own shock wave. We will see how that can be quantified. We'll take that as a case for DOS. So you can do it anywhere. This is pictures from Settles. So this is Gary Settles himself barbecuing on a summer day, sitting next to a heater on a winter day, or somebody lifting a pack of ice cream from a freezer in a supermarket. So all of these can be visualized. So it is very real. All of us actually are sending up our own little plumes. You can in fact set up a Schlieren which is sensitive enough to get the speech coming from my mouth. You can rub your hands and see the air coming up. In fact, if from the cell phone, if you play music, you can visualize the sound waves too. All of this is very, very possible, and done routinely. So there is no mystery about it anymore.
So the artistic use
No, these are real pictures. These are real pictures. This is top here. All you need is a simple LED and two polished mirrors. That's all. Nothing more.
So,
Please.
so the projectile.
Sit down and ask.
The projectile image that you showed, the one that's going at Mark,
Yeah.
the ones that going at Mark 4.75.
Oh.
You basically visualized a shock that's around it.
Yes.
Do you think there'd be any similar image recognition if you did it with a heat gun, maybe? Like since there is a certain relation between pressure and temperature, do you think there'd be a similar relation if you did it with a heat gun and maybe if you observe both of them together?
So essentially, suppose I had a hair dryer, right? So you can get a very nice thermal jet with a hair dryer, but obviously you won't have a shockwave. Like I said, a shockwave is a sudden rise in pressure. Essentially, it is a shockwave. The rise time is like this. So this is what you see the pressure when you go through a shockwave, an end wave, right? So this end wave is a very high change in pressure, and that on a time scale that, like I said, is just 2 microseconds. So that is visualized as a very sharp, dark or white, when inverted, line in a slither. Other than that, this as far as wave and such things are concerned, yes, you can, other than shock waves, you can mimic density change due to pressure by density changes due to temperature. And that is part of the $64 million question. In fact, how do you decouple a density change which is brought out by pressure as opposed to temperature? So if I had heated that sphere and dropped it, I would have sent it through this, I would have got all of it except these shock waves. Everything else would happen.
Thank you, sir.
So these are actual pictures. So let's just recap before we go on to that. So basically, Schlieren image is an image. Shadowgraphy is actually a shadow. Second thing, remember. This cuts off the light with a knife. I didn't go into all the details. In fact, in Seru's book, you'll see that the theory of Schlieren itself is dealt with over 50 pages. I think that's a little too much for this. So, but you can see it if you are interested. And there's no cutoff in shadowgraphy. And this shows the deflection angle. A shadowgraph shows the actual displacement because it's a derivative. This is a little more difficult to use. This is easier to set up. What you see, why do I need anything else? But what we saw was all the visualization. That's qualitative. You say it looks nice, it looks lovely, it has a barbecue there. But can you get the temperature of the barbecue there? No. You can only say that this is the extent. So if you wanted to quantify, none of these will do except interferometry, which I already said is way too expensive, difficult, vibration prone. Essentially, it relies on path difference. So you, for a Mach-Zehnder interferometer, would take quarter of this room to set up just to visualize the density field of a candle. And if you so much as breathe it around it, the density is off. So that's not really viable. So you require what's called, what was invented, it says 99, but it's actually 2000, sorry, by Gerd Meyer at DLR. He said, background oriented Schlieren. This comes from the German again, Hintergrund Schlieren pattern. So basically he's saying that if you have a background and if you can use that to find out a Schlieren, then probably you can get the density. So how does that work? Look at this. The basic theory of or the principle is that the image of any object which you take with your cell phone, say, is a convolution, it's a mathematical process, between the object which you are imaging, which can be one of your friends or any object out there, and the transfer channel. Essentially, if I pull out my cell phone and take a picture of the class, but if I have a flame or a hot air column here, then it's a convolution of the hot air column and your image, as opposed to nothing being. So you are seeing this all the time, like I already said. This aircraft jet engine exhaust. You can see it's not that it's a blurry picture. You can see that it's quite sharp here. That became blurry thanks to the exhaust going there. Essentially, what we got was a convolution of the hangar door there and the exhaust which is staying in front. So what is the argument? So the argument, if you knew what you are imaging and you have the image already in your device, you can obviously back out what was the property of the transfer. Fair enough. You have a pair of variables, a pair of equations, because you know the object, you know the image, you only need the transfer channel. A, B, C, you know A and C, you can know. And they are related by the now familiar Gladstone-Dale equation. Anyway, so what do you have to do? It is as simple as ABC. You just take the picture of a structured background in the absence of a flow. So what do I mean by structured background? Structured background can be anything which has some variation enough to create a picture. So essentially, I don't want this surface, but anybody else, anything else is a structured background. So it can be you. The only caveat being, I take a picture of you, then I set up a flow and take another picture of you, but none of you should move between them. So you will see how easily you can do that. It is very later. So don't get put off by the man. So essentially, it is a background plane. Typically in labs, we use actually a formal structured pattern. We use a dot pattern. Dot patterns, all of you know how to generate. Ideally, it should not be regular. Why should it not be regular? There are mathematical reasons for it called peak locking and such stuff. Let's not go there for the moment. It has to be random. So you can pull out your MATLAB. I'm sure most of you are familiar with MATLAB. Use a random number generator, convert it, put a threshold, convert it to black and white. You get a dot pattern, which is simple enough. You get a dot pattern. You put a camera here and just take a picture of it. Then put your hair dryer, hot plate, or anything in between. Take another picture. So let us watch in a little bit. We'll come back to it. So that's just the process. Now, what am I saying there? To our familiar epsilon, which we remember. So I'm calling it epsilon here to avoid complications. So epsilon here, that is the deflection angle, is proportional to the change of the density gradient, right, over the length of it. So what only assumptions I'm making? The only assumptions I'm making is that you have imaged this field in the absence of the flow. So I've taken a picture of the class in the absence of any flow out here. The background doesn't move, class is frozen, and I put up the flow and take a picture again, and the flow is small compared to that distance. Why is this required? That's just because the deflection caused by that should have to travel significant distances because it's a small gradient before it becomes a displacement, essentially. So that's all you're saying. So essentially, if I could have two pictures of this dot pattern and I could find the amount by which those dots are displaced, because all of you agree from the aircraft exhaust picture which I showed, it will displace the background. So if you could just find out by some magic tool how the dot was displaced, then obviously you know what you are getting are displacements of each dot, and these are the density gradients at each point. So that's exactly what this is saying. And the density gradient, the displacement at each point normalized by the gradient of density, right, over y along z, is essentially related to the distances. Don't even worry about this. For now, just say you have two pictures and you found the displacement. Let's see how we can do this in actual practice. Right? So we want to create a density gradient. So I think I'll not mess around with the hot air and all that. hot air is turbulent, it waves, someone comes into the room, is unpredictable, depends on temperature. So I will take a shock wave, very easy to create, very repeatable, very reliable, and you have simple shock tables to tell you what the angles are. So I take a cone cylinder, this is something like a bullet, but very sharp nose bullet. I put it in a wind tunnel. It's a picture of the 1 foot wind tunnel at NL. I believe some of you will be going on a visit to. So I start the flow. The flow is at twice the speed of sound. I will get a shock wave. I know that from basic isotropic relations. The flow will then expand over the shoulder and give me an expansion fan, more flow features. Now, so if I see the cross section of the tunnel here, what do I see? This is my body, which I've kept here. And these are the windows. You are seeing the windows here. So I put a dot pattern, which I print out in my simple laser printer. Put a light source behind it, right? That's because I don't have enough light. Why do I not have enough light? Because I want to take a picture with the highest shutter speed possible. Why is that? Because there's so many vibrations around due to the tunnel running, and if you have too much vibrations, the background is going to move, the class is going to move, right? So you want to keep it steady, so you take very short exposure pictures. The shorter the exposure, the higher should be the light source. That anybody who has imaged with a smartphone knows that, right? Otherwise you get fuzzy pictures or dark. So I just take 2 pictures of that. So what do I get? I get this. What you see here is the edge of the window. Right? I just got the dot pattern without the flow and with the flow. Now visually, because there are so many dots, you cannot even make out that anything has happened. What happened? Nothing happened. So then what do? I want to find the displacements. Now there's a mathematical method called cross correlation, by which 2 images or 2 matrices, you want to find out the displacement. You can just take the cross correlation of B with A. Simply put, you don't even need to worry about the math, thanks to MATLAB. And you just go to MATLAB, say, IMREAD of A, P is IMREAD of B, and then you say XCOR2, A and B, and you're done with it. You don't even bother to put the, just leave it on default. What do you get? You get this. So suddenly, out of nothing, no optics, no fancy arrangements of light path, this, that, bothering, you got the gradient of density field. You want to get it vectors. Well, I'm oversimplifying it. You have to put a few more lines of code in MATLAB, but that's also all. You can actually ask for a cross correlation, this one in MATLAB Central or something. You will get someone's package and you can just do this, just like that. So you get vectors. These are vectors. The vectors point towards the direction of lower density. That you can reverse that. Be with A or A. No problem. So you saw the shock wave right from the leading edge. You saw the expansion fan. And you got essentially what you were getting by the slither. That is the density gradient field. Right? That displacement gradients are yeah, these are displacements. Yeah. So essentially for each dot is displaced by some amount due to the density field. Some are barely displaced because there is no change here in the reflector. It's a high pressure, but there is no change. So when they are displaced, the dot will be found by the cross correlation. So it essentially gives you a vector in x and y displacement, and that vector is what we set out here. Here, yeah. Essentially, the displacements are the gradients of density at every point. So the delta y's, those are all delta y's. Essentially, I'm showing in one direction, but that's in 2 directions. 2D cross correlation. So delta x, delta y are essentially the density gradients in x and y. So what you are getting with all those optics, you are very easily getting with just mathematical methods and so you actually all of you can go home and try this. Why? You pull out your smartphone, I've done with my own smartphone, it works.
Mr. Surya has worked there, he did some works with the image analysis.
Yes, yes. So it's very, very simple. In fact, you can take it against a tar road or a concrete patch, for instance. If you don't want to print out anything, you can take it against maybe not this wall. You need the wall to be dirty enough so that you have enough features on it to cross correlate. A very clean sheet won't do it, right? You don't want like this. So you just take two pictures. You can take the tree leaves if you want as a background, as long as they are not moving by wind or anything. So, and you will exactly get whatever is the, you can put up your hair dryer in between and you get a slur. So you got a slur at no cost. Now,
But it's mathematical representation, but you can't really see something.
you can see it on screen.
Screen,
Yes.
but you can't really see.
Yeah, you won't see it in, actually all you will see in your images are just
that's
these.
right.
Yeah. Unlike Slur, you will, but if you have this online, as soon as it takes the image, you process it and you will see. So, let's tell you what is it I've done. Now, I want to find the density. Now, these are density grades. So, those of you who are mathematically inclined will just say that why don't we just integrate? Yeah, simple. Integrate in line integrals. But line integrals are messy. You will get like vertical, it aligns itself along vertical lines. Number one. Secondly, yeah, every point, it's a continuum. So every point in the field has in a way contributed to another point. Right? So essentially, basically there are connections between all these points. So you should convert it to a field equation. So all you have to do, we already have gradients, take a gradient of the entire gradient field, and where you get your Poisson equation. This I'm sure you know from fluid mechanics. The right side is the source term. This is a PDE. You can solve it using PDE toolbox, or if you want to show off your mathematical muscle, you can solve it by Ehrlich's over relaxation methods. You can just put the boundary conditions and essentially you solve it. So you can actually get the density field. This is what is here. This is actually the density field of over a cone at Mach 2. Now, some of you will say this doesn't look very clean. Why doesn't it look very clean? Because we had this tunnel here, we put the cone here, and what you are seeing is line of sight integrated. Essentially, you are seeing through the whole path. So you have this whole volume of density through which you are seeing. But now, if I take a point on this, while all of this is density, if I take a point on it, each point on this is line integrated through the depth. So it's really of no use to me. But I will say, I will essentially make use of one. Whenever a field cannot be considered 2D or infinite in the line of view, we have something called tomography, which will help you solve, take slices of that. I hope none of you have been unfortunate enough to be inside an MRI machine, but that is exactly what they do. Essentially, they take views at different angles and find slices, right? So that is what we will proceed to do. Again, so this is with the basic principle of tomography. You have, actually in the MRI machine, you have an emitter and a receiver, but here it's just a background and a camera. This is the flow. I have shown it circular for simplicity in the math, but it need not be circular at all. So essentially, each of these is generating one line and registering on one line of pixels of your CCD of your smartphone or camera. So basically, if you take enough number of views, you can take a slice, because that's simple to understand. You take, if you just had one, it's line of sight integrated. You have two, you have broken into 4 quarters. So basically, you have a 90-degree slice. You take n number, usually they never take more than 9, though nowadays there are machines which take 36, to get as thin a slice. This is essentially the basic principle which was invented way back in 1917 by a guy called Abel, a mathematician, who is called Abel transform. He took it as the peeling of an onion. So those of you who would have visited the kitchen would have seen, if you cut an onion, you see the essentially a hemisphere with interleaving leaves. So if you take a vertical slice, this is exactly what we are going to do. Now we are going to say that as we say, think of this as a lead rod. Think of these as X-rays when you go to the airport or something. Now the portion which has lead in it will absorb the X-ray, so lesser X-rays will reach the detector. Those which have no lead will reach. That is how your X-ray is done on your bones or anything like that. That's exactly. So if we do this correctly, essentially, this is a parallel beam and then it's angular scanning, and we can get this. So I am showing the result first. So essentially, I recreated the entire shock surface, the expansion surface on that. This all only metal. Notice I have used no hardware other than the camera and made the printout for the pattern. Right? So it's all essentially possible to do. So we can even see how to do this. Now comes, it's like in mutual funds they say everything and say subject to market risk, right? So now comes the math. So try not to sleep. So we will keep it very light and easy. So this again is your, say, lead rod. Amount of radiation coming through. Essentially, more is absorbed, so more is absorbed, and then nothing is absorbed, so you are back to that. This is what you would see at the detector. Think of it in the same way. So essentially, you have basically what's called a radon transform, which is what was seen in 1917. You see radon transform and the Abel inversion. So
one question on the previous one.
Sure.
When you move it by theta, theta, theta,
right,
you are essentially not focusing at a single point in time. So the flow has to be stationary.
Excellent observation. That is why, as of now, BOS is only for staying. You could, in principle, make it unstable by putting 9 or 12. It has been done already. But for simple flow. But in a tunnel, you don't have optical access at 12 points around the clock. You have only one pair of windows.
Yes.
So you have to, and you cannot rotate the window, so you rotate the object. Now, you see, I was being very clever and I took an axisymmetric object. So I have one image, but I say it's the same as n number of images. If you rotate a cylinder even 360 times, every degree you have the same angle. So doing it for complex, say the space shuttle kind of thing, is a little tougher. We'll see that has also been identical. So what deflects down here will deflect up there. They cancel.
Yes, sir, but the background is essentially outside the windows itself.
Very, very nice question. You have been listening. So, that means that's why it is done. Two things are taken into account. One is the shutter speed is very, very high, right? Not very, very. No, not nowadays. Like 10,000 of a second, right? So you are essentially not allowing the background to blur. Now, it's also assumed there is no heat plume rising within the tunnel. And finally, look at the density change due to a shock wave, right? It is like several orders of magnitude than that due to the heat, say, coming out of my mouth. Right? So you will not see the displacement. In fact, you do see it if you are very, very careful. Sorry about going back, but yeah. This is essentially the noise due to the setup. Here. There shouldn't have been anything here. This is the noise due to the setup. Noise due to small thermals, due to vibration of the tunnel running, due to, nowadays we don't click the picture, it's all remote configured. So it's, all of these are noise. Now you can take 10 sets of these pictures, average them out, the noise disappears. Because that's random noise. The mean of a random event is 0. But that will remain. So these things remain. As long as you're doing steady.
Yes.
You do unsteady, time result, all bets are out. That's why it's trickier to do unsteady. So this is called a sinogram. What is the outcome on your detector, which is your CCD, of what came through. Essentially, and that's the rotation matrix. Don't worry. So essentially, the projection transform is this. Basically, it is trying to find out, given a sinogram, what is the original which created this kind of depression which you saw, I of theta, essentially. So, we will then skip to the next and say, how do you solve this? You can do it by a number of ways. There is a brute force inversion technique, also known as the Abel technique. But you will see in that, again I'm skipping all the math here, there's a 1 by r term. And where is the r? The r essentially is here. This is r, going out to the center. So as r tends to 0, 1 by r tends to infinity, you get a mess in the center. So brute force inversion is not what you are looking for. So you need some better techniques. You have many different techniques, iterative techniques. There is called algebraic reconstruction, the ART. There are many variations of ART. There's a modified ART. There's a little more small modified ART. So many ARTs, as long as you don't put an F before it, I think you're fine. So there is also,
These are available in MATLAB.
some you have to code, some you have to modify. Nowadays, of course, if not in MATLAB, it's there in MATLAB Center. So it's not a big deal. If any of your students wish to do it, I can send you my MATLAB code. But mind you, it's still a research code. So those of you who are startup inclined, bear in mind, there are commercially available NDV, PIV, PSP systems, but no BOS system. I mean,
These are very costly.
yes, but this is dirt cheap, but still there is no system. I know I have been approached, but there has been no inclination to make such a system and put it out there. So those who are startup inclined can write their own BOS code and probably sell it back to your university. So think about it. So you can have Fourier technique, you can have back projection technique, but what we are going to use is a filtered back projection technique. Now all of these are very nicely given in the book on tomography by Kak and Slaney, K-A-K and Slaney in 1987. But I will not go into those details here, and you know, the math is a lot. Whenever you see people who run out of regular symbols and start making their own fancy ones, you know there is something nasty in the math. But you don't need to know all that. Essentially, what I'm trying to tell you is, as far as you are concerned, to make a usable system, a MATLAB toolbox and a camera is all that you need. Essentially, you don't need to worry about that. But just for the sake of it, what we're going to do is essentially, we are taking a 1D Fourier of each row of my camera CCD. So I have m rows by n columns. So essentially, I take a 1D Fourier, and you should remember the set of 1D Fourier in R, the ratio, of the Redon transform of function is the 2D FFT of that function. So as long as you adhere to this law, you will find that if you know the Fourier transform of all the projections, meaning all around the clock, which for an axisymmetric you need only one, you can choose to say in reconstruction, I am assuming that I have 12, say, just for the heck of it, because the 12th one is the same, or 10th one, 6th one is all the same as the first, as long as the flow is axisymmetric. So basically, if you know the projection, then the inverse Fourier transform is what gives you the field itself. So once you get this field, you get that nicely reconstructed one which you saw. Then after that, extracting slices from that is child's play. You take MATLAB, you take TechPlot, and so you have to essentially stack the projections into a block, and then from the Fourier extract this. You will notice I am not going too deep into this. If you have any questions, I'll be happy to answer them. But for you to know, you need to know what is the math behind that. But for doing the process, you don't need the math. Essentially, this is what we did. So if you have too few, the reconstruction is blurry, right? And you need some kind of sharp impulse function in order to make sure that your edges are clean. Otherwise, one set should not bleed into the next. Right? So you use that. And the response to an impulse function is so essentially you are changing your B of theta like this. You add up the densities at all angles, you get your laminogram, which is another word for saying the 2D of the sinogram. So you can get this. Now you see I have sliced it in the central plane. Don't worry about this. This is just the edge of the window which you saw in the first one. So you have your actual density normalized by rho infinity. You have these are actual density values in the central plane. I can get you anywhere you wish, even off axis. So now I have with nothing more than a dot pattern and a camera and math tools, I have extracted actual density values which you could not get easily earlier from Schlieren. And you can get it on even a complex flow like that. Is it good? Yeah, you go to front tables and see. This is kind of matching it. So,
It's the cone angle of the.
yes, so essentially it is the shockwave angle, and this is from cone table SIMS. And you can extract values from there and see it matches. You can see from isentropic relation the value. I cannot go too close to the wall simply because of diffraction over the small. Essentially, if the rod is very small, then obviously your curvature is too much. So light rays bend, so I cannot go too close to that. But it is matching very well. So just to recap, what did we do? We obtained two images of a structural background in the absence and presence of the flow of interest. We calculated the density gradients by using the cross correlation algorithm. It's called. Then you converted it to a Poisson equation. This is on an elliptic cone. So on an elliptic cone, essentially, like I said, we don't have 12 windows. So what I do, I keep it at an angle. So now you will imagine an elliptic cone already has only one plane of symmetry, top and bottom. If my major axis is along the x direction, and if I tilt it, obviously I'm losing even that plane of symmetry, because then I no longer have any symmetric plane. So what do? Since I don't have ability to change the camera at different ways, I turn the cone itself, and that you can just put it on an arm and rotate it such that this tip remains at the same point, but the rest of, basically, I'm not Jackie Chan, so if I could, I would move my elbow in a circle while keeping the tip of my finger. So it's the same setup, the rest of it. So this is how it looks. This is like a regular Schlieren. So you can see it is moving. The major axis is now vertical. Here it was horizontal. So you can see at different angles. So I can, for this, reconstruct it. This looks almost like CFD. In fact, it's better than CFD. So for essentially the density layers at different points over the field. Right? How good is it? So one of these is CFD. One of these is from the experiment. I leave you to guess which is which, but they are almost identical. Right? So now we can become a little more ambitious and go on to say an explosion. So I think some of you in this audience were there yesterday when they talked about shock waves for needleless drug delivery and that kind, right? I assume some of you were there. Essentially, so basically it's a blast wave, right? A blast wave, as opposed to a flat top shock wave, has an exponential decay from the overpressure, right? So you can think of it as a point explosion. So you can have nuclear explosions or solid explosives, blah blah blah, and it's all for the theory. And you can you are looking at these blast waves to characterize large explosives or explosions, and how to see how from the shock wave, essentially history on this. So Taylor, they said when the first atomic bomb was exploded, they said G.I. Taylor just looked at the thermal plume and calculated the kiloton yield. And Fermi, who was standing on top of the tower, threw down some paper balls and looked how far they drifted. And he knew how he was far from the explosion, and he calculated the yield. They both were right to the first decimal, which the supercomputers at Los Alamos took 3 days and worked out to the second decimal. So essentially, using simple gas dynamic rules and simple blast wave equations, you can very easily know how a shock wave propagates and find out the strength of the shock wave. Right? So these blast waves, you have seen all of this yesterday. I will not bore you with it, from food preservation to biomed to gene therapy. I mean, shock it. So basically, what is it as far as I am concerned here? It's a transient flow. The shock blast wave just goes through. It's non-stationary. So the application of any technique is very, very challenging. Now, if you capture the density field, it allows you an understanding of the physics, but it's very challenging in terms of illumination and imaging, because the blast itself gives you so much light. You have to somehow find a way to kill that light. And we use the WS technique along with the laser source. So how do you create the blast? This was really cool until the license got yanked from us. So this is from Nobel Industries, and this is their igniter, and this is a blasting tube. Essentially, you can cut lengths of the tube. It's internally coated with HMX, and stick it into the end of this. This produces a spark. This spark, once it comes, we just went and got one of those mosquito killing bats, and the same spark can be produced. But you cannot buy this tube anywhere, and you cannot definitely buy it without the license. So if you want to replicate this, forget it, unless you want to have a visit from people in uniform. So basically, you set up the whole experiment. I'll not bore you with this. This is a laser, because you need a light which is short enough in duration. The laser pulse is 10 nanoseconds, so it's good enough to freeze the flow. You have background pattern again, and we just used a mirror in order to create a path. So those are all the electronics to time in between the time you press the trigger to when you see the blast. This shows the setup, right? So this is again your Nobel Industries setup, and this gives you a blast, and this is the light source coming through to and lighting up the background. So this is how it will look. So watch carefully the panel on this right. So essentially, as soon as you press this, the blast wave will come out of there, and this just shows the timing diagram, how to coordinate all the electronics essentially. So you have, this is a regular slither, right? You visualize it, but you couldn't measure. So this is another close-up of the same regular slither. This is done by Professor Jagadeesh, who was here yesterday. And these are at different instants. If you just freeze the film, you can see how the blast wave is coming out of it. So it makes it very, very tough to get quantitative information in a flow like this. So then we said, okay, again we are back to a friendly dot pattern. Flow, with the flow. Obviously, we have two problems here. One problem being the blast itself, right? You cannot see through it. The laser, while very powerful, is not more powerful than this blast. Of course, we can make the laser more powerful, but then it would burn through the background too, so it would not help. There's a problem, you will not get any data here. So this is not, this becomes a case of a non-transparent flow. And see here, just for those who are interested in it, there is an, though this has been imaged at 10 nanoseconds, figure out how many zeros after decimal, still you can see the turbulence in the flow. So essentially it is such a highly turbulent flow that you can see the distribution distortion even if it has been freeze framed, right? So, I mean, 1 microsecond is 1 megahertz. So, you figure out at what framing rate it has taken. But yet, so it shows the challenges of these kind of flows. However, we get the equivalent of, again, the density gradients, vector the lower density. I show for comparison the due to the shock. So you can see here again, and the density gradients at 40 microseconds. You recollect how it was looking in the actual film, and at 50, right? The white portion is the tube due to which you get that. At 60, at 70. So now I've got the gradients. I'm ready to do the reconstruction, and it looks very nice and fancy. You can see actually the precursor flow. You can see basically the blast surface. You can see the cap which is moving outwards, and essentially all the flow features. The right side is just a slice at the center. It looks nicer in this. So basically you have the contact surface. This is essentially like for a bullet or something like that. There is no actual object going through. We did try to put some pins to go out. It's too dangerous, bouncing around the lab. So we stopped that. So essentially, if there was a bullet, it would have penetrated through and gone. So you have a web shock, you have underground jet, light flow, flash. These are all what those are looking at the shock. Right now, we're just looking at the technique. So you can see the different surfaces. You can see this translucent surface, which is the flash wave. This is at a different time. It's at 93 seconds. So you can see how it is evolving. So you are seeing what the different variations in density are, and mind you, these are all actual density values. And you compare with some numerical simulations by Jiang et al. You can see the same kind of precursor flow, the ring and such at the corresponding times, right? You look at Klingenberg, and this is for a bullet. So the only difference between the two is the bullet has now penetrated the basic the muscle wave, whereas here we do not have a bullet. It's firing blanks essentially. So the vortex ring is the same, the mark disk is the same, and the turbulent air gas interface is the same. Those are densities. This is just a shadow graph. So this shows that you can actually now extract the density field through this. Mind you, I won't get any data here. I already said that due to the flash in the first 30 microseconds. So, but I can extract now values from the density field. And once I extract the values from the density field at different time instants, from 53 to 127, I can plot this. And those who have gone through a couple of courses in shockwave can recognize the Rankine-Hugoniot relations, so you can match that. So you actually got usable density data to do this. Now, why do they want this? Say, for example, you want to estimate the effect of a flash wave on a structure. You can get the actual over density or over pressure from this and see whether your structure will withstand the flash wave, which you could not have just by using a slurry. Short out and blowing it away and check. So this shows all the relations, but it is not bottle network. Okay. And now we put to compare with the training data. That's all you do in a regular neural network, like where they say data science requires no background and come become a data scientist. So essentially you're feeding it tons of data, and you expect to get a match. It's like. But usually these kind of neural networks never work other than if you're studying completely non-physics driven flows. Then it works. You say that I'm looking at some random patterns, then it works. But if it's physics driven flow, it will give you very unphysical data. So you have to put in one more layer. So what do? Essentially you have your neural network again to compare to training data. But basically, auto differentiation can allow you to compute all the gradients. So UAX is very UAX. So this it does very, very efficiently. Anyone who used the neural network toolbox knows that. So basically, I present here the physics-informed neural network. So physics-informed neural network use a simple deep neural network to solve either forward or inverse problem. Now this is all from regular literature. This is from Wikipedia. You can go and essentially what it says is that when you take some x and t and try to evaluate u, you are losing the underlying physics. So if I were to impose the underlying physics in the form of equations, right? Navier-Stokes. So I call it that the Navier-Stokes laws or an experimental law. Or I know from experiment that this is what has to be. So I force the neural network to conform to this too, in addition to just merely training as was done earlier. Then I use basically the derivative to evaluate what is the loss with respect to Navier-Stokes, with respect to the experiment. So basically I'm doing what's called a physics-informed neural network. So now we saw the BOS is an inverse problem, right? So you have an outcome, the image, and you're trying to find out the density which caused the image. So basically, we use supplemental information to construct the flow, which is called Gladstone-Dale equation. But many times, you know that the Gladstone-Dale equation, we don't know the actual constant for the mixture of gases or something like that. So when we reconstruct it, we force that into some bracket, or we put smoothing terms. You will get errors in the density. You do get them. So instead, basically it's a regularization problem. We'll not go there. That's more. But basically, physics-informed BOS essentially forces the BOS measurement also to be that way due to the neural net itself. You have essentially solved either Euler, those cases Euler was sufficient, there's hardly any viscous flow, say the cone cylinder, right? And you can even get velocity pressure there. So basically, what does this plot show? It takes your x and r, your axial and the radial component, and you are mapping it to the field of interest, rho, UV, and energy. And the BOS model is embedded in the data loss term. We are using Euler and irrotation as the equations for the physics class, and we are forcing the internal conditions. So with this, you can actually get the density field also. I mean, the pressure and velocity fields also. So starting again from a dot pattern and a camera, we went to getting density fields. Using the density fields, we used it to train a neural network such that we got even the velocity and pressure fields. So this, for this I will stop here, this particular topic, because it's much more involved. So you'll have to kind of get it rather than run. There's so many variants of BOS. There's pulsed illumination BOS, high framing rate camera BOS, there's color BOS, there's BOS used to try to do velocimetry, there's retroreflective background BOS, natural background, like I said, grass and trees. There's reference free, there's no background BOS. There's free surface BOS, there's even smartphone BOS, launched done by a Japanese group. So you can look it up. It's a smartphone BOS. There's a huge number of literature on BOS. Right from helicopter vortices to jets to exhaust, explosions, high temperature gas flows, underwater shockwaves, scramble. If I try to do it, there are like nearly 500 papers on BOS applications. So I will run out of space if I try to list one. So, with that thought, I leave you to say about the conclusions. So it's a very easy to use visualization tool as far as visualization is concerned. And you can get quantifiable data as we already proved. It's very simple and it allows applications in environments where you cannot set up mirrors and lenses and all that. You get the quantitative information anyway using any kind of off-the-shelf camera is nothing required. The importance for complex flows like those blast waves cannot be overemphasized. You can get things which you would not have. And you can even reconstruct the flow as we saw using machine learning. So essentially that's all I have. And if you have any questions, we have to answer. Thank you.
So I have a question. We said we have shadowgraphy, we have shear, and we have interferometry. So can we say that the quantitativeness will soon be bridged if we keep working on machine learning? So the kind of, we said the interferometry is very cumbersome to use and complicated, but that's the only available quantitative method. But slowly using machine learning, physics informed learning, in the course of time, this could be a de facto.
Absolutely. Basically, in a physics-informed neural net, what you need is some way to enforce the physics laws. Level, place, and get accurate data. Then you won't need the rest of it. It's not possible, and that's why you go to the physics. So yes, in fact, pin-enforced machine learning is probably the hottest topic there is. That's the reason.
From the dot pattern, how we will identify the shock is strong or weak?
Okay. So the dot pattern itself just gets displaced. The amount of displacement, as we saw, the epsilon, the angle through which it does, is proportional to the gradient of the shock. Now, so at each point in the field where you saw those vectors, some vectors were long, some were short. So the long vector, essentially, that's the vector, say, u hat, is ux squared plus uy squared. Okay? So essentially, there you know that there has been a stronger density gradient. Now, from there, as a first cut, you could just integrate and find, like I said, the value. Otherwise, you could convert to a Poisson equation found. So you would know whether the shock is strong or not. You would know that is strong or not just by looking at the length of the vector itself. Right? You would not be able to quantify the shock value, but you would definitely know that this is a strong shock, this is a weak shock, because in the same picture, you would have some long vectors, you would have some short vectors. Does that answer your question?
If anyone else has any questions? No?
So I have one more question. Usually we use it for high speed flows, shear and effect. For low speed, people are experimenting with infrared cameras and small changes in the images due to conductive currents and so forth. So is there a threshold like which technique we use and where is even preferred?
Okay. So basically, there's a fundamental difference. So an infrared camera, typically the kind you can buy from Flip, can go up to measurements. It actually converts the heat signature. It essentially solves the radiative equation. You know, the perfect black body when you take a Stephen Boltzmann and it solves that. So you can go down to as low as 0.1 Kelvin. It's a direct measurement. However, again, mind you, it will give you a block. So if I point an infrared at you, right, what stuff you see on the Predator movie or Schwarzenegger is still very far away. You don't get that yet. So what you see, you'll see a blob. And that blob temperature is, right, mean temperature of the blob, essentially. So it's showing how much radiation is it throwing out. So Schlieren is for places where you can go, the light rays can go through. Whereas an infrared camera can take a picture of your pressure cooker, say, and say it's hot. Schlieren can only look at the plume coming from the pressure cooker. It cannot see the pressure cooker itself because the rays are depend on the deviation.
Medium. Thank you.
Anyone else?
Sure.
Does anyone else have any questions?
Yeah.
How we will decide like how much should be the intensity of light to get the good dot pattern?
Actually, that is just trial and error. First time I used one of those arc lamps, the kind you see in weddings, right? So that's actually non-Gaussian. those things don't really matter. Because finding a cross correlation, what you need, picture is binarized, right? It's black and white. So even a 2-bit picture, 2-bit representation of a picture is enough. You don't need fancy 24-bit or anything. So essentially, it's looking at a small area. In that, you are breaking the image up into chunks. And basically, what does a cross correlation do? If you have, I'm overshooting my time, but if you have 2 images, you basically break up the image into small chunks. So you are formatting this and this corresponding image taken after that cutting. So this is essentially you are trying to do a convolution. So what a cross correlation does is it remembers that convolution in the spatial domain is equal to multiplication in the frequency domain. That's a theorem in mathematics. You can look it up. So essentially, I take the FFT of this say A1 and take the FFT of say say B1. So I take these 2 FFTs and multiply them in the frequency domain. Easy enough. Take the frequencies and multiply the corresponding coefficients. I take the inverse FFT of it, right? And what I get back, those coefficients are essentially my correlation function. If you plot that, you will see over that small chunk which you have taken. If you have taken a 16 by 16, you will see a peak. And since you know the peak should have been at the center, wherever the peak has moved.
Anyone else has any questions? Okay, over to Amshu for the.
Thank you very much, sir, for your valuable scientific inputs. I now request Dr. K. Vijay Kumar, HOD of Department of Physics, to felicitate our guest.